Hi folks, and welcome back to Physics with Captain Rod. I'm making this video to help you understand how to use the concept of velocity and a velocity graph to calculate the change in position of an object. So what we're going to do, we're going to imagine this car here moving along, and at t equals 0, this car is moving at 3 meters per second. In addition to that, due to the driver applying the gas pedal, the car is also accelerating at 2 meters per second And again, when you look at this in something like a textbook, you usually see those units written like 2 meters per second squared. I really like to write the units like this. To me, it just better reminds me what that 2 means. You know, after a second goes by, this car's velocity is going to increase by 2 seconds to 5, and then it's going to go to 7, and then it's going to go to 9, and so forth. I think that these units written like that better, at least for me at least, better help me understand that. All right, so what we're going to do here is we're going to calculate the change in position for this car after 5 seconds using our velocity graph. So the first thing we typically do is, let's construct the graph. Actually, let me back up. That's not the first thing you do. The first thing you typically do is define a set of coordinates to work in. And I'm just going to do this. At t equals 0, I'm going to say the car is here. I'm going to put a coordinate system right here. I'll put it in green, x, y. We don't really need the y coordinate, but I'm going to go ahead and put it there anyway. Now that I have defined a coordinate system, we can say that at t equals 0, x is equal to 0. It's important to realize this green coordinate system is fixed. It's not moving. The car is leaving it behind, so to speak. And then the x coordinate of the car is changing and getting larger and larger and larger. All right, let me get back to my velocity graph. So at t equals 0, you ask yourself, what's the velocity of the car? 3 meters per second. So 1, 2, 3 meters per second. I'll just put the units up here, put a dot here. Now, 5 seconds later, the car is going to be going considerably faster. Now, how much faster? Well, let's calculate it. And we can do that using the acceleration. So acceleration is equal to change in velocity over change in time. The acceleration, I'm going to rewrite this equation over here, is known to be 2 meters over seconds squared. And that's equal to a change in velocity over our change in time, which is 5 seconds. And I'll leave this as an exercise to the reader here, but if you multiply both sides by 5, you get 10 meters per second out of this. Now, this 10 meters per second, that's not the velocity of the car, that's the change in velocity of the car. The car started at 3 meters per second. So 5 seconds later, 1, 2, 3, 4, 5. The car is now going 13 meters per second. That's up here somewhere. It's not important that we get this exactly right. If the acceleration is constant, that means this is a linear function. And again, this is now the point 5 seconds and 13 meters per second. Again, for those wondering, where did the 13 come from? The initial velocity was 3, and we added our change, our increase, which we got from here. Now, the delta x for the car, like how far did the car go? And hopefully you've watched my graphs about how to do this. The area under this velocity curve here, this area right here, is going to give us that delta x. This shape is a trapezoid. The left distance is 3. The right distance here, this vertical side, is 13. So the area is going to be 1/2 3 plus 13, and then times the width, which was 5. And unit-wise, these are in meter per second times seconds. This will come out into meters. I'm going to go ahead and just grab a calculator and run that. What do we got here? Oh, I can do that without a calculator. Let's see, 16 divided by 2 is 8 times 5. This is 40 meters. So this car will have displaced by an amount of 40 meters. Now, we can kind of sketch this graph. Now that we have a coordinate system, by the way, this first point is here. And just some reminders here. If you're not moving, this graph would look something maybe like this. Constant velocity would give you a linear graph. That's not this case. This increasing velocity is going to give us something that's concave up. So this point here, that distance, 40 meters. This would be the coordinate. Where to go? 5 seconds, 40 meters. Now you might say, well, this distance looks smaller than this. Well, it doesn't make sense to even compare them. This is a distance in meters. This is on this graph, this distance is representing a velocity, 13 meters per second. I put this at kind of an arbitrary location, but the scales for these two graphs does not make sense to even compare vertically. So anyway, again, the point of this video is how to use a velocity graph to calculate the displacement, the change in position for an object, which is in this case undergoing constant acceleration. I hope that this helps. Have a great day.